During the operation of a fluid system, process variables such as pressure, flow, level, and temperature may remain relatively constant over a period of time. Under these circumstances, the system is said to operate under steady-state conditions. However, operating changes and process disturbances are a common part of system operation. And when changes occur, process control systems may make adjustments that result in a new set of steady-state conditions. The period of operation that occurs between one set of steady-state conditions and another is known as dynamic operation. Process disturbances and operating changes are a common part of fluid system operation. The way that a system responds to changes can depend on different factors or characteristics. Two important characteristics that can affect a system's response to changes are resistance and capacitance. Resistance can be thought of as an opposition to flow. Capacitance can be thought of as the ability to store energy. While these terms are commonly used in discussing electrical circuits, they can also be applied to other processes and systems. For example, in this simplified liquid system, a container serves as a reservoir for the liquid. The energy for the system is the liquid's head, that is, the pressure caused by the depth of the liquid. The resistance in the system is caused primarily by a valve that opposes the flow of liquid from the container. When the valve is closed, the resistance is high and there's no flow. But if the valve is opened, the resistance or opposition to flow decreases and liquid flows from the container. This system's capacitance or ability to store energy is determined by the size of the container. The larger the container, the greater the ability to store energy and the greater the capacitance. These same basic characteristics can also be applied to gas or vapor systems. For example, in this simplified gas system, the resistance is caused primarily by a valve that opposes the flow of gas from a pressurized cylinder. The capacitance, or the ability of the system to store energy, depends on the storage capacity of the cylinder. Now, in a thermal process, that is, one involving heat, resistance and capacitance may be somewhat different. Here, a flame is used to heat a beaker of liquid. In this arrangement, the wall of the beaker represents the resistance, since it resists the transfer of heat from the flame to the liquid. The amount of heat, or thermal energy, that the liquid is able to store represents the capacitance of the system. Regardless of the form that they take, resistance and capacitance can greatly affect a system's response to operating changes. Changes that occur in a fluid system typically do not produce an immediate visible effect. In fact, it can take anywhere from a few seconds to several hours for a change in one part of a system to produce a noticeable change in another part of the system. The reason for this time delay has to do with the physical characteristics of the system. For example, in this simplified liquid system, a valve offers resistance to the flow of liquid from a container. The size of the container determines the system's capacitance. With the valve closed, there's no flow through the system. Let's see what happens when the valve is opened. We'll plot the effects of opening the valve on this graph. The vertical axis of the graph represents flow, and the horizontal axis represents time. When the valve is opened, the flow of liquid from the container increases rapidly at first, then levels off at its maximum value. The curve that's formed on the graph is often referred to as a dynamic response curve. It illustrates a basic fact about a system's response to operating changes. The response is gradual, not immediate. Other processes exhibit similar responses to operating changes. For example, in this heat exchanger, steam is used to heat water for a process. The steam flows through coils in the water heater, while the water flows around the coils. At the moment, the temperature of the steam entering the heater is 400 degrees Fahrenheit, and the temperature of the water leaving the heater is 200 degrees Fahrenheit. Now, suppose the temperature of the steam suddenly rises to 500 degrees. Even though the steam temperature increased suddenly, the water temperature will remain unchanged briefly, then increase slowly. It's easier to see why the water temperature changes this way by plotting the temperature changes on a graph. On the graph, the vertical axis represents temperature, and the horizontal axis represents time. When we plot the steam temperature, we see the sudden increase from 400 degrees to 500 degrees. This type of disturbance is commonly called a step input. But when we plot the water temperature, we see that there's a delay between when the steam temperature increased and when the water temperature first started to rise. This delay is called dead time. It can be thought of as the amount of time required to transfer energy from one point to another. We also see that once the water temperature started to rise, it rose gradually, not suddenly. That's why the shape of the water temperature curve is similar to the dynamic response curve that we saw earlier. The total amount of time from when the steam temperature changed until the water temperature reached its maximum amount of change is called lag. Lag is caused by the combined effects of dead time and other process characteristics, such as resistance and capacitance. In this process, the transfer of heat from the steam to the water was delayed because of the resistance to heat transfer in the steam coils and because of the water's capacitance, or the ability of the water to store heat. While resistance and capacitance are two of the major factors that affect a system's response to operating changes, they aren't the only factors. Another common one is related to distance. For instance, in the water heater example, the water temperature was measured just downstream from the heater. But if the temperature were measured farther away, it would take longer for a change in water temperature to be detected. On the graph showing steam and water temperatures, the added distance from the heater to the indicator would show up as a longer time delay between the increase in steam temperature and the increase in water temperature. The greater the distance between the heater and the indicator, the greater the time delay. Physical characteristics such as distance, capacitance, and resistance can all delay a system's response to operating changes. For that reason, you need to give a system time to respond to changes before you try to determine whether or not the system is operating normally. Complex systems can take time to respond and settle out when changes occur. Knowing how physical characteristics can affect a system can help you determine if process variables are changing as they should. Also, since changing conditions at one point in a system can affect other parts of the system, you need to be familiar with the location and operating characteristics of system components. In this topic, we focused on changes that occur in a fluid system during dynamic operation. We identified several different factors that can affect a system's response to operating changes, and we examined the effects that those factors can have on a system. Now let's try some practice questions that relate to this material. Now, in a thermal process, that is one involving heat, resistance and capacitance may be somewhat different. Here, a flame is used to heat a beaker of liquid. In this arrangement, the wall of the beaker represents the resistance, since it resists the transfer of heat from the flame to the liquid. In this heat exchanger, a sudden increase in steam temperature will cause the water temperature to increase slowly. It's easier to see why the water temperature changes this way by plotting the temperature changes on a graph. On the graph, the vertical axis represents temperature, and the horizontal axis represents time. When we plot the steam temperature, we see the sudden increase from 400 degrees to 500 degrees. This type of disturbance is commonly called a step input. But when we plot the water temperature, we see that there's a delay between when the steam temperature increased and when the water temperature first started to rise. This delay is called dead time. It can be thought of as the amount of time required to transfer energy from one point to another. We also see that once the water temperature started to rise, it rose gradually, not suddenly. In a plant, many different variables are monitored by process instrumentation. One of the most commonly monitored variables is pressure. While pressure itself is a key process variable, it's also closely associated with other process variables such as flow. Pressure can be measured using a lot of different devices. We'll focus on two pressure elements that are commonly found in pressure measuring instruments: a board-on-tube and a bellows. Both of these devices convert changes in pressure to mechanical motion. A board-on-tube pressure element is basically a curved hollow tube. One end of the tube is closed. It's connected to a mechanical linkage, which in this case is connected to a pointer that's used together with a scale. The other end of the tube is open so that the pressure from the process is exerted inside of the tube. When pressure is applied to the board-on-tube, the tube tries to straighten out. The movement of the tube is transferred through the mechanical linkage to the pointer. When the pressure being applied to the tube decreases, the tube curls up. This causes the mechanical linkage in the pointer to move in the opposite direction. Another pressure element that's used in industry is a bellows. A bellows is basically a movable accordion-shaped tube. In this arrangement, one end of the bellows is connected to a pressure source, while the other end is connected to a mechanical linkage that's used to move a pointer up and down a scale. When pressure is applied, the bellows expands. As the bellows moves, the mechanical linkage moves the pointer as well. When pressure is removed, the bellows contracts, and the pointer moves in the opposite direction. In general, bellows elements are very sensitive pressure detectors. Also, they can be set up to measure pressure in different ways. For example, the bellows in this arrangement is designed to measure pressure changes that occur inside of the bellows. The bellows is connected at the bottom of a chamber to a pressure source, so any change in pressure acts on the inside of the bellows. Here's a different arrangement. In this case, the bellows is attached at the top of the chamber. The bottom of the bellows is sealed, so the pressure that's applied at the bottom of the chamber acts on the outside of the bellows. A bellows can also be set up to measure the difference between two pressures. Here, the bellows measures the difference between the pressures that are applied at the bottom of the chamber and the top of the chamber. In a fluid system, it's often necessary to determine how much fluid is used, moved, or produced. To provide this information, different types of flow measurement devices are used. Not all flow measurement devices work the same way. Some measure the actual amount of fluid that passes through them. We'll call them direct flow measurement devices. Others measure process conditions that are related to flow, such as pressure. Then they convert those measurements to flow indications. We'll call them indirect flow measurement devices. This nutating disk meter is one device that measures flow directly. It gets its name from the action of a disk located inside the meter. The word nutate means to wobble or roll about an axis of rotation. During operation, fluid enters the meter through the inlet. The fluid flow causes the disk to rotate much like a slowly spinning top. As the disk rotates, specific amounts of fluid are trapped above and below the disk. If a change in the process causes the flow rate to increase, the disk rotates faster, but the same amount of fluid is passed along with each rotation. A counter mechanism counts each rotation of the disk to keep track of how much fluid is passed through the meter. While direct flow measurement devices measure the actual amount of fluid that flows through them, some indirect flow measurement devices rely on some type of energy conversion to indicate flow. One of the most common devices used for indirect flow measurement is an orifice plate. An orifice plate is basically a plate with a hole or orifice in it that's used to restrict the flow of fluid through a pipe. More specifically, the orifice plate causes an energy conversion to take place. As fluid flows through the opening in the orifice plate, its pressure decreases and its velocity increases. The conversion of pressure to velocity causes the pressure on the downstream side of the plate to fall below the pressure on the upstream side. A device such as a differential pressure, or DP cell, measures the difference between the two pressures and provides a corresponding flow rate signal. If the flow rate through the opening in the orifice plate increases, the difference between the two pressures increases as well, and the DP cell provides a signal representing a higher flow rate. By converting energy from one form to another, an orifice plate creates a differential pressure and enables the flow rate of a fluid to be determined indirectly. Accurate level measurement helps ensure that proper amounts of materials are maintained in plant systems. One device that's sometimes used to measure level in fluid systems is a displacer. A displacer operates on the principle of buoyancy. This principle states that when a body is immersed in a fluid, it's lifted or buoyed up by a force that's equal to the weight of the displaced fluid. To see how the principle of buoyancy applies to a displacer, we'll use this illustration of a displacer attached to a container of liquid. Liquid levels equalize in containers that are connected together, so the level inside the displacer's chamber stays the same as the level in the container. A weight hangs in the chamber and is connected through a linkage to a transmitter. The higher the level of the liquid in the tank and the chamber, the more liquid is displaced by the weight, and the greater the buoyant force. The increase in buoyant force causes the weight to rise slightly in the chamber. The linkage transfers the movement of the weight to the transmitter, which in turn transmits a signal representing the level to an indicator or a controller. Another way to measure level is to use a device that measures head. Head can be thought of as the pressure exerted by a liquid as a result of its height or depth. For example, the pressure exerted on the gauge mounted near the bottom of this container depends on the depth of the liquid. Now, the density of a static liquid will also affect pressure, but in this case, the density doesn't change. If the level of the liquid increases, the pressure exerted on the gauge increases as well, and the gauge converts that pressure to an indication of level. Temperature is a key process variable that's commonly monitored in plants. Temperature can be measured using different types of temperature measuring devices. One of the most common temperature measuring devices is a thermometer, such as this liquid in glass or liquid-filled thermometer. It consists of a glass tube which contains a liquid and a calibrated scale. This particular scale is in units of degrees Fahrenheit, but other scales, such as degrees Celsius, are commonly used. A liquid-filled thermometer operates on the basis that most liquids expand when they're heated and contract when they're cooled. Increases in temperature cause the liquid to expand and move up the tube. Decreases in temperature cause the liquid to contract and move down the tube. The level of the liquid in the tube indicates the temperature of the substance being measured. Another device that's often used to measure temperature in industrial applications is a thermocouple. A thermocouple consists of two wires made of dissimilar metals, which are joined at one end so that they produce an electrical voltage. The other ends of the wires complete a circuit to a measuring device with an indicator. When the temperature sensed by the joined ends changes, the voltage generated by the wires changes as well. That voltage is detected by the measuring device and displayed as a temperature indication. In this topic, we focused on the measurement of four common process variables: pressure, flow, level, and temperature. We looked at several devices commonly used to measure these variables. Now let's try some practice questions that relate to this material. Another pressure element that's used in industry is a bellows. A bellows is basically a movable accordion-shaped tube. In this arrangement, one end of the bellows is connected to a pressure source, while the other end is connected to a mechanical linkage that's used to move a pointer up and down a scale. When pressure is applied, the bellows expands. As the bellows moves, the mechanical linkage moves the pointer as well. An orifice plate is a plate with a hole in it that's used to restrict fluid flow through a pipe so that flow can be measured indirectly. In this arrangement, a gauge that's mounted near the bottom of a container provides a level indication based on the liquid's head. That is, the pressure exerted by the liquid as a result of its height or depth. A thermocouple consists of two wires made of dissimilar metals, which are joined at one end so that they produce an electrical voltage. The other ends of the wires complete a circuit to a measuring device with an indicator. When the temperature sensed by the joined ends changes, the voltage generated by the wires changes as well. That voltage is detected by the measuring device and displayed as a temperature indication. In this heat exchanger, steam is used to heat water for a process. If the temperature of the steam entering the heat exchanger suddenly increases, what will happen to the temperature of the water leaving the heat exchanger? In this arrangement, a single valve is used to control the flow of liquid from a container. Suppose the valve is moved from the fully closed position to the fully open position.